To add matrices, they must have the same dimensions, the same number of rows, and the same number of columns. As shown below, add the elements in corresponding positions. So we're going to add this matrix to this matrix. First we add this number to this number. 2 plus 3 is 5. Then we add 4 to negative 3 to get 1. We add 5 to 0 to get 5, and so on. Find the indicated sum. All right, A plus D. So we're going to take this matrix. So that is 1, 0, 3, negative 2. And we're going to add D, which is this matrix. That's going to be negative 3, negative 1, negative 2, negative 4. Okay, so top left, 1 plus negative 3 is negative 2. 3 plus negative 2 is 1. 0 plus negative 1 is negative 1. Negative 2 plus negative 4 is negative 6. A plus C. So A is 1, 0, 3, negative 2, plus C, and that is 3, 5, negative 1, and 2. All right, so 1 plus 3 is 4. 3 plus negative 1 is 2. 0 plus 5 is 5. Negative 2 plus 2 is 0. And finally, B plus C. So B is negative 2, 5, 4, 6. C is 3, 5, negative 1, 2. All right, so negative 2 plus 3 is 1. 4 plus negative 1 is 3. 5 plus 5 is 10. 6 plus 2 is 8. And here you have all of the answers. As with addition, matrices must have the same dimensions in order to subtract them. As shown below, subtract the elements in corresponding positions. Alright, so we take this 5, we subtract negative 3, and we get 8. Here we take negative 6 minus 7, so that's negative 6 minus 7 giving us negative 13. Negative 1 minus 1 is negative 2, and 4 minus negative 2 is 6. Or you can elect to change the subtraction sign to addition and treat the negative sign as a scalar that has a value of negative 1. When doing so, you need to multiply all terms in the second matrix by negative 1. Then you add the elements in the corresponding positions. So we change this into an addition problem by changing this negative into a plus sign and then changing the signs of each number in this matrix. So negative 3 becomes positive 3, 1 becomes negative 1, 7 becomes negative 7, and negative 2 becomes 2. Then we can just go ahead and add these together. And we end up with this matrix here. Find the indicated difference, A minus D. All right, so we're going to have a 2 by 2 matrix. Top left minus top left, 1 minus negative 3 is 1 plus 3, which is 4. 0 minus negative 1 is 0 plus 1, which is 1. 3 minus negative 2 is 3 plus 2, which is 5. Negative 2 minus negative 4 is negative 2 plus 4, which is 2. All right, moving on, we have D minus A. So, negative 3 minus 1 is negative 4. Negative 1 minus 0 is negative 1. Negative 2 minus 3 is negative 5. And negative 4 minus negative 2 is actually negative 4 plus 2, which is negative 2. All right, and there's our answer. Let's do this last one by treating the negative sign as a scalar with a value of negative 1 and changing this into an addition problem. So we have B, so negative 2, 5, 4, and 6, plus negative C. So we're going to take each number in here and switch the sign. So negative 3, negative 5, 1, and negative 2. Now we add them together. Negative 2 plus negative 3 is negative 5. 5 plus negative 5 is 0. 4 plus 1 is 5, and 6 plus negative 2 is 4. And there we go. There is a special type of matrix known as the zero matrix, whose elements are all zeros. They come in all shapes and sizes. A few examples of zero matrices are given below. This zero matrix has a size of 2 by 2. This is a 2 by 1, 3 by 3, 1 row by 4 columns over here. Do you remember the identity property of addition? It allows us to add 0 to any number, and we are left with the same number. A plus 0 equals A. The zero matrix will allow us to do the same things with matrices. For example, what if we took matrix A from our last example and added a zero matrix to it? What would happen? Alright, well, as you can see, adding a zero matrix, a 2 by 2, to the original matrix A does not change the answer. The result would be the same as matrix A, meaning matrix A would be unchanged. The zero matrix proves that there is an identity property of matrix addition. When a zero matrix is added to any matrix of the same dimensions, the matrix does not change. Below are a few examples. The zero matrix also works as an identity property of matrix subtraction. When a zero matrix is subtracted from any matrix of the same dimensions, the matrix does not change. Below are a few examples. Perform the following operations on the given matrices. 2a plus 3b. Alright, so the first thing we're going to do is multiply this matrix by 2. We're going to multiply this matrix by 3 and then add the results together. So 2a is a times 2. So I'm just going to write it all out. So we have 1, 0, 3, and negative 2 plus 3 times negative 2, 4, 5, and 6. All right, so the first thing I'm going to do is multiply the scalars in. So 2 times 1 is 2, 2 times 0 is 0, 2 times 3 is 6, 2 times negative 2 is negative 4, plus, and we have 3 times negative 2, which is negative 6, 3 times 4 is 12, 3 times 5 is 15, 3 times 6 is 18, and now we add those together. So that is going to be 2 plus negative 6 is negative 4, 6 plus 12 is 18, 0 plus 15 is 15, and negative 4 plus 18 is 14. And that's our answer. All right, next we have D minus 4C. So D is that matrix there, negative 3, negative 2, negative 1, and negative 4, minus 4 times C. So I'm just going to multiply this by 4 right away. So 4 times 3 is 12, 4 times 5 is 20, 4 times negative 1 is negative 4, 4 times 2 is 8. All right, so now negative 3 minus 12 is negative 15, negative 1 minus 20 is negative 21, negative 2 minus negative 4 is going to be negative 2 plus 4, which is positive 2, and negative 4 minus 8 is negative 12. So here's the answer for part 2, and there is the answer for question 1. All right, there's our solution for question 1 and for question 2.